right? So these are the multiplicity of the poles. And how can we define the integer k here? There is no way under Maple or the symbolic toolbox we cannot define an integer. So we have to try different values. For instance, k equals to 1, minus 1, 2, and minus 2. Try several numbers and see whether you can get something with a certain formula. So for z equals to 0, we can easily find the residue of it because it is a double pole here, so we have to use this command to find the residue of it. And the result is 0. And for z equals to plus or minus k pi, where k does not equal to 0, we have to try several values. For instance, k equals to 1, minus 4, 4, minus 3, 3, and so on. Then we can form a loop here and find the poles, find the residues to the pole here. And see whether we can find the result, useful result here. So these are the results which correspond to the value of k there. For the value of minus 4, we have this result, and 4 which are the same as this one, and this one. So it seems that we have k in the denominator and pi in the numerator. And if you check the signs, for the first one we have negative here and negative here. And for this one we have negative, but this one is positive. So we have to use results like this. So we can summarize the result summarize the formula from the result. But we have to do this by hand.
How do you come up with a c equal k times pi from the equation? How do you come up?
Sorry, that one you mean?
Is it c equal k times pi?
This one?
Yeah.
I think this is the point which makes the sign z equal to 0. Right?
From the equation, right?
From the equation, from denominator. It's because it is a pole, so we have to use the derivative in this way. And we cannot define integers in Matlab, so we have to try several values and extract certain formulas from it. Okay. So sometimes you have to use manual manipulations. And now we come to the topic of partial fraction expansion for a rational function. So this kind of function we call it rational function because it has a numerator and denominator polynomials. It is like something like the transfer function of a system. So it is a rational function. By the word partial fraction expansion, we mean that we can expand the original rational function by something like this. X, E, by a sum of terms like this. And there are some, if there are repeated poles, we have a repeated pole, we have to write something like this, pi squared of x plus pi cubed, something like this terms. So this kind of expression is called the partial fraction extension, and it is useful in taking the inverse Laplace transform. I think you have already already relatively early control causes. And before we perform partial fraction extension, we must find whether there exist certain poles or zeros which can be cancelled. So what we need to do is to find the greatest common divisor of the numerator and denominator. And this one can be obtained by GCD, which is greatest common divisor. We can find it. And then if it is a dynamic term which contains the variable of x, then they can divide a and b separately by the polynomial c, so that we can simplify the original rational function. And these are the mathematical details. I do not want to go into too much about it. So suppose there are two polynomials. One is for numerator and the other one is for denominator. So now I want to check whether these two polynomials are co-prime, which means whether there exists a common greatest common divisor which contains x. If there isn't a greatest common divisor which contains x, we say that the two polynomials are co-prime. And this is the term to denote the denominator. So how can we check that? What we need to do is declare the x variable as a symbolic variable first, and then extract the two polynomials in the natural way like this. And once we have done that, we can call the GCD function and see whether we can have a dynamic greatest common divisor between the two polynomials. So this is the function called A have to use. And finally we find that the greatest common divisor is 5 plus x. So it contains x. So we say that the two polynomials are not co-prime. So we have to simplify them each, such as A is A divided by B. And we can simplify it in this way. And now A divided by B is unique and simplified result. Any problem?
And what do I think like single A divided by B? Is this?
I think you can do it. I think you can do it. But here I just want to show the idea of greatest common divisor between two functions.
So the common divisor is the first time was x plus 5, right?
Yes.
Why you? I didn't see why you need after.
After that, I explain it to you then. What I did is you have two polynomials A and B, and they have a greatest common divisor. So what I did is I divide this one, divide A by x plus 5 and divide B by x plus 5. Because x plus 5 is a factor in A, so we can cancel that divisor. And this one also cancel the factor in B. And now the topic is how can we find the partial fraction extension to the rational function? And these are the formulas, and I do not want to talk too much about it. These are if minus pi is a k-multiple repeating pole of the function, then we have to use partial fraction extension like this. And we have to use this one to calculate the numbers there, the numerators. We have to. So this is not residue. These are the numerators of the partial fraction extension to be evaluated by this formula. And based on the fact